Hey, it's Dr. Mitch, ready for the second half of the Drugs in the Nervous System lecture. Hope you took your 5 minute break and got your notes all ready for some Cornell notes here. Let's start off by having a little recognition memory test. So, which one of these is the fastest modes of administration? You'll notice here we got smoked, drink, or skin popping, which is just another expression for a form of injection. Which one of these would you pick? Well, of course, you'd pick smoke, right? It's going to go right into the lungs, and that blood's going to go right to the brain. That's going to be the fastest of these three. I won't put like hair splitting ones like injection and smoke or something like that. Uh, Point is just that you know the different routes of administration and how fast they go. So now we're going to get into the nervous system organization, and this is an important set of distinctions, and we're not going to go nuts on memorizing every single neuron, but I just want you to have these general categories so when I'm talking about how a certain drug works, you'll know what I mean when I say it. So we've got the peripheral nervous system and the central nervous system, and as their names imply, the peripheral system is on the periphery, going out all over your body, right? And then that's divided into two parts, the somatic system and the autonomic system. And the autonomic system is divided into two branches as well, sympathetic and parasympathetic. Now, these are artificial distinctions, right? Your nerves are all connected. It's all connected. You don't have to do a hallucinogen to know that. But the bottom line is that's completely separate from the central nervous system, which is the spinal cord and the brain, right? So each nerve is going to go from some peripheral point, make its way all the way to the central nervous system somewhere, and then get up to your brain or the spinal cord. All right. So peripheral, outside, central, right down the middle. Now, the somatic system, as it suggests, is all about your body, right? It's going to reach out to the soma. The autonomic system is going to have these two different branches, and the distinction between these two branches is important. And again, it's a little artificial, but the notion is we have the sympathetic, right, essentially going to work for arousing things, and the parasympathetic working towards lowering arousal. And we have techniques for strengthening both of these, and they're really worth knowing, so you could change your arousal as you see fit. So let's get into the sympathetic autonomic nervous system, and this is right part of that peripheral system again. And what this does is essentially handle when you're increasing arousal. So what's going to happen? Your pupil's going to be dilated, right? Your eyes are going to open up wide so you can take in as much information as possible. Your salivary gland is inhibited. It's not time to eat, right? It's time to the 3 F's, fleeing, fighting, or mating. And you're really going to be getting ready for action. So breathing is going to be more rapid, right? You're going to have breaths that are going to come faster. And so obviously one good way to calm yourself down would be to slow your breathing, right? But when the sympathetic is aroused, you're going to be breathing more rapid. You're going to have an accelerated heart rate, right? You'll show tachycardia when the sympathetic nervous system is stimulated, a sign that you're increasing arousal. Digestion is inhibited, right? It's not a good time to lie down, right? You got to get running. Bladder is relaxed, right? So if you see a bear, it's not time to carry a bunch of water around with you. If you got to run, go ahead and, what a surprise, let it all go. And then the penile erection vaginal moistening is inhibited, right? It's probably not time for this ideally right now either, because odds are high you got to get rolling. Meanwhile, the parasympathetic essentially does the opposite. Now we're going to be decreasing arousal, right? So the pupil's going to be constricted in the sense that, your eyes aren't wide open. It's slowly getting more mellow. Salivary gland excited, like if you're getting ready for a nice meal. Breathing will be less rapid. Heart rate is going to decrease, decelerated, right? Digestion is excited. Bladder tension is increased. And then penile erection vaginal moistening is excited. Right? Now this is a revealing thing when we start getting into sexual effects of some drugs. But the bottom line is some drugs don't go very well with uh, sex because there's too much activity in the parasympathetic system. If you are having some kind of sexual dysfunction, often it requires either decreasing sympathetic activation or increasing the parasympathetic activation. And we'll get into that when we have a sort of how to have a good sex lecture. Well, so when we think about stimulants and sedatives, let's think about how would they work. A stimulant drug would be stimulating the sympathetic, right? The autonomic responses are going to heighten. You're going to have increased heart rate and things like that. But another way a stimulant drug might work is to inhibit parasympathetic responses. So make the part of your nervous system that would normally slow you down not be able to function as well, or both. And in fact, for a lot of drugs, it is both. Sedative or depressant drugs usually go the opposite. So they're going to stimulate parasympathetic autonomic responses and inhibit sympathetic autonomic responses, or both. All right. So sedatives are going to decrease arousal. They will stimulate the parasympathetic responses. Stimulant drugs are increasing arousal. They're stimulating sympathetic responses. Make sense? So here's a nice item. If you were fleeing, right, if you're running for your life, which part of the nervous system is going to be heightened? Which part is going to be activated? Is it the sympathetic, the parasympathetic, or the central? And obviously, it's the sympathetic. Okay? Now, I'm going to have a trick question on the test, and I'm going to say which part is inhibited, and you'll have a different answer, obviously. All right, here's a nice item as well. If your digestion is working well, is it the parasympathetic that's stimulated, the sympathetic, or the central? And again, the parasympathetic would be activated. How this is a mellow, relaxed situation where you can sit and digest your food. All right. Now the book goes into wild distinctions about the major sections of the brain, but all I want you to know is the back, the hindbrain, the midbrain, which is right down the middle, and the forebrain. And you don't need to know the subcategories or anything like that. You'll hear me talk about the forebrain as the frontal cortex a lot of times because that part is often altered in response to some drugs, and that's the part that has evolutionarily developed later and is important for making good decisions. And it's curious how some drugs that interfere with the frontal cortex also make it, unfortunately, harder for you to quit using drugs. So a good thing to know. But bottom line is if you know the back, you know the middle, and you know the front, you know the hindbrain, the midbrain, and the forebrain, you guys will be fine. No need to memorize these other structures yet. All right, here's a little review just because we did get that neuron rather quickly in the previous lecture, but the bottom line is the cell body is the bulk of the neuron and it contains the nucleus, and that's going to be the telltale indicator, that little dark spot. That's also where the mitochondria are, right? The powerhouse of the cell, the one thing everybody seems to remember from high school. Dendrites are usually relatively the shorter appendages, and they're the ones that receive a message from the outside, either an environmental stimulus or the neuron that's ahead of it. Dendrites are often the postsynaptic part of that synapse. And the axon is the relatively long one where the information is traveling down. And you saw they're often myelinated, and that makes the message go faster. And it's going to send a message out to the muscles or send a message to the next neuron. All right. And there are two ways a neuron can be impacted: excitation and inhibition. When a neuron is excited, it emits a greater number of impulses per second, right? It's got to be completely on or completely off, right? But it could come faster, and that's a sign of excitation. In contrast, if a neuron is inhibited, it emits a fewer number of neural impulses per second. And in fact, some drugs will make it so that a neuron will fire less rapidly or even be less likely to fire at all, and that would be inhibition. Right? Now, after a neuron fires, we've always got that little bit of a refractory period. Once it shoots, right, it needs a second to let all the ions get pumped back into their regular place for the resting state. And so that refractory period is an inherent part of how many messages a nerve can send in a second. All right. We've got tons and tons of neurotransmitters that have been identified, and some of these function as hormones in other parts of your body. And I don't need you to memorize all these yet. We'll know which ones are involved as we go over each individual drug. But in the long run, on the average, I just need you to be able to recognize these when you see them. So you know that acetylcholine, all the cholinergic neurons work in the acetylcholine system, and it's involved in memory usually, stereotypically, but again, we'll learn this down the line. Norepinephrine, you know that one is adrenaline, maybe from the hormone literature. Dopamine, and that one often has a lot to do with pleasure, and a lot of the drugs of abuse are active in the dopamine system, say cocaine, for example. Serotonin, which is a pretty complicated one, but we saw it has a big impact on mood. We'll see it when we talk about the antidepressants, although I'm not thrilled with the serotonergic model of depression. And a lot of the hallucinogens have some activity there, and we'll learn those real soon. GABA, which is a sort of anxiety-related, loosely, neurotransmitter. And the endorphins, another sort of source of pleasure and analgesia that's natural in your body. But again, just be able to recognize these if you saw them. So if I said, which one of these is a neurotransmitter, you would pick these and not some crazy other word I'm going to make up. And then a very important part of psychoactive drugs to understand the blood-brain barrier. So thank evolution to our divine power, we have a very intricate set of meninges, a set of tissue that surrounds your brain so that not every single thing that gets into your blood necessarily makes it to your brain. And believe me, we're all alive because of this. So in order for a substance to make its way through the blood-brain barrier, it's going to have to be fat solubles to get in through there. And then it'll basically only reach the brain from the bloodstream if it could get past this blood-brain barrier. And yes, fat solubility is the key. So THC, for example, is fat soluble and it can make its way through. Lots of other molecules can end up in your bloodstream, but fortunately do not make their way to your brain. And then important contributors to reactions to drug are tolerance. That is, you're born with a certain propensity to react to certain drugs, and experience tends to also contribute to how tolerant you are with drugs. And we're going to talk about two of these, but these are not the only sources of tolerance. One is metabolic, and the other one is cellular. The other name for metabolic is dispositional, and this is just basically what's the rate that the liver is going to break down the drug. And truth be told, it sounds kind of funny, but your liver can kind of learn. Your liver can get a little more efficient and start to metabolize drugs more rapidly if they've been exposed to some of them previously. And what a cool way to learn, huh? In contrast to cellular, which is also known as pharmacodynamic, and this is actually a change at the receptor site. So a receptor can essentially become more sensitive, or your nerve itself will lose some receptors in pharmacodynamic tolerance, and so then it will be less sensitive to the drug as you develop tolerance to it because of a change at the cellular level. So really these are about changes in your metabolism or change at the neuron itself. With that in mind, I want to really emphasize a double-blind placebo-controlled design. And this is going to be part of how we separate what's a genuine pharmacological effect of a drug from what is an expectancy effect. What is an impact simply because we think we have the drug. And if you've ever slipped a placebo beer on one of your buddies who then acted drunk, right, that's a classic placebo response. Number of us end up conditioning to certain cues. So you'll notice folks who act as if they've already had a serious alcohol effect after only one sip of alcohol. Odds are high that's partly at least a conditioned response and certainly an expectancy response. So individuals administering the drug do not know whether the substance administered is actually the drug or a placebo, right? So they're blind. It's a placebo administration. Individuals receiving the drug do not know whether the substance received is actually the drug or the placebo. That's great. Now, why would it be double blind? That's when the experimenter doesn't know either. So I might have somebody working in my lab and I don't tell them which drug it is. I just label some things A and B, and then they administer it so that way they don't give any cues away. They don't hand somebody a drink and go, oh, here's your drink, right? As if they know it's not real. That would wreck our assessment of the response potentially. And we'll get into this more when we do some of the alcohol work where we talk about the balanced placebo design. But my point is really, let's make sure we understand that some drug effects are really related to us expecting we've received a drug rather than pharmacology itself, and this is how we separate this out. Now, obviously, some of the animal work, whether it's ethical or not, doesn't have the same problems with expectancy, but we do try to make sure we administer saline or something like that so that we know from our causality argument with random assignment and experimental manipulation, we can tell if a drug really has an effect or not. Hey, sorry about that. I didn't want to end so abruptly, but the bottom line here is you can do this. All right, so there is a lot of material. We did go kind of fast. Feel free to go back through it again. Make sure you use those Cornell notes. Write yourself some questions. Take your time answering them. I'll get a crossword puzzle up, and I will also post a link to the Kahoot questions. This is as physiological as things are really going to get, and once you understand these, the rest of the lectures are going to be easy. I really appreciate you guys hanging tough with this, and I'll be posting the next lecture soon.